Okay, Miss Teasley here. Today we're talking about rational functions and their graphs. Um, Remember when you see the word rational, because you'll see that word come up a lot in this class. When you think about rational, think about the word ratio. And how do we write ratios in math? Well, you can write them as a fraction. So notice how it says a rational function is a function f of the form p of x over q of x. So a rational function is made up of two polynomial functions. It's a fraction. All right, so it says where p of x and q of x are polynomials, what's special about a fraction is that the denominator cannot equal 0. Therefore, the q of x polynomial cannot equal 0. All right, so this reciprocal function, this is your basic parent function of a rational function. So the most basic one, 1 over x. So let's kind of look at this 1 over x and fill out this table. So you see it's a graph. It's not a continuous graph. There's this gap or break in the graph. Continuous meaning that if you try to draw this graph, you're going to have to pick your pencil up. So I'm tracing it. Then I have to pick my pencil up and then I have to trace this part of the graph. So that's what the word continuous means. All right, so at 0, the graph breaks apart. All right, I have to kind of pick my pencil up. So my domain, so if you notice, my domain is going to be all real numbers, all right, except 0. So it's going to be all the x values except 0 because there's no x value at 0. So the way that I write this will be from negative infinity to 0. All right, with the parentheses because 0 is not included. Union 0 to infinity. And this is same for the range. You have that break in the middle on the y-axis. So this will be from negative infinity to 0 and from 0 to infinity. So the domain and range are both the same. So here at 0 is undefined. 1 over x, the graph decreases on both intervals. So in the beginning, I was tracing the graph. When you trace this graph, you always trace from left to right. And notice how if I trace this, I'm decreasing. So the graph is decreasing from negative infinity to 0. And then if I start back up here, it's also decreasing from 0 to positive infinity. So, sorry, it's decreasing. It's decreasing on both intervals. All right, so from negative infinity to 0 and 0 to infinity, they're both decreasing. It is discontinuous, so it's not continuous at x equals 0. Vertical asymptotes. All right, so you have this vertical asymptote, which is this line that I'm drawing here. That vertical asymptote is the y-axis. So the y-axis is a vertical asymptote. That's the line that the graph gets closer and closer to on both sides, but it doesn't actually cross it. And then you have this, let me use a different color. All right, because we got a lot going on here. So you have your vertical asymptote, which we draw our asymptotes with dashed lines, and then you have this horizontal asymptote, all right, which is the x-axis. So again, asymptote is a line that the graph gets closer and closer to, but it doesn't actually cross over. It's like a brick wall. All right. Whereas a horizontal asymptote is the end behavior of the graph, and we're going to talk about that when we get to our example. So determining asymptotes. How can I determine these asymptotes without even graphing the actual equation itself or graphing the actual rational functions? All right, so this is how you determine asymptotes. It says to find asymptotes of a rational function defined by a rational expression in lowest terms, use the following procedure. So lowest terms, you definitely have to make sure that you simplify it all the way. It says vertical asymptotes. Find any vertical asymptotes by setting the denominator equal to 0 and solving for x. If a is a 0 of the denominator, then a line x equals a. All right, a meaning any number is a vertical asymptote. So let's talk about that. So I'm going to skip this other asymptote section for now, and we're going to jump down to this first classroom example. It says finding the asymptotes of a rational function. So here we're going to be talking about vertical asymptotes. The first thing it says state the domain of the function. Give the equations of any vertical asymptotes and holes for the graph of each rational function. So I'll explain to you how all this, what a hole is and how we get our vertical asymptotes. All right, the first thing you want to do is you want to factor the top and the bottom. So when I factor this first fraction, I get x minus 1 times x plus 1 because that's a difference of squares. And when I factor the denominator, this is x plus 2 times x plus 1. So the first thing you do is you find your domain. My domain is all real numbers except any numbers that make my denominator 0. So the numbers that would make my denominator 0, well, what number plus 2 would give me 0? All right, x equals negative 2. And here, the number that would make my denominator 0 in this parentheses would be negative 1. So I'm going to write it as x equals negative 1. We'll come back to that. All right, so x equals negative 2 goes to the first parentheses, x equals negative 1. These are the two numbers that x cannot equal. So when it comes down to your domain, the way that you'll see it written is that x cannot equal. So that's a cannot equal to symbol. And you would just put negative 2 comma negative 1. This is your domain. Well, these two numbers represent something. So these two numbers are excluded from your domain, but they either represent a vertical asymptote or a hole in the graph. If it cancels out, so when I go back and look at this problem, if you notice I have an x plus 1 at the top and an x plus 1 at the bottom. Because the x plus 1 cancels out, which goes with this equation x equals negative 1, this means that x equals negative 1 is going to actually be a hole in the graph. So this is a hole. The vertical asymptote is what's left over. So what didn't cancel out, which is x equals negative 2, this is going to be your vertical asymptote. So vertical asymptote is x equals negative 2. So I'm going to put this into Desmos and let's see if we can see all of this in Desmos. So x squared minus 1 over, all right, give me a second. So I'm going to put y equals fraction. You have to hit the division button. This is x squared minus 1 divided by x squared plus 3x plus 2. So the first thing we had that we said there was a hole at x equals, what was the value? At x equals negative 1, there's a hole. All right, well, negative 1. Let's see if we can get the, first I want to make sure I type in the equation correctly. X squared minus 1, x squared plus 3x plus 2. All right, so let's see if I can put it here. Let's see if I can change this. So you know how you can change this to a table if you hit this gear button. And if I hit this table beside it. So now I have a table. Well, notice how at negative 1 it says it's undefined. You don't actually see it on the graph, but there's actually a hole at x equals negative 1. All right, there's nothing there. There's going to actually be a hole as in like a little circle in the graph. And that x equals negative 2 is undefined because if you notice that's your vertical asymptote. That's where the graph breaks apart. Right? So it's kind of like the original reciprocal function. You have this vertical asymptote at x equals negative 2. So let me kind of sketch that so you know exactly what I mean when I say a hole. So if I had to do a rough sketch of this graph, I'm saying there's a vertical asymptote at x equals negative 2. So I will say that's negative 2. And then at negative 1, there's some type of hole. Let me make sure I get this back up here. Negative 1. So somewhere down here, at negative 1, there's actually going to be a hole, a gap. Oh, sorry about that. It wouldn't be that big. All right, let's do this again. So -1, there's a whole, so there's an open circle there. And let me see if I can get that. So down here, let's see, -1. Let me see if I can touch it at -1. Go back to home. So let's see about here. If it'll show up. Sometimes it'll show up for us. All right, it's not showing us the graph, the whole at -1. All right, and then you have the other side. All right, it looks like this. All right, so this is your graph. This is a sketch, an open circle here, a vertical asymptote at -2. All right, you have to be able to identify the vertical asymptotes and the holes without, using a graph. And as you can see, if I looked at the graph, I wouldn't see that there was a hole. I mean, you could tell there's a vertical asymptote, but you wouldn't be able to identify the hole. So that's why algebraically you need to know how to do this. All right, let's go through the next example. Let me erase this big old circle so I can see this. So that was -2. So here, go through the same steps. I need to factor. So when I factor this, I get y equals at the top. The greatest common factor is 2, and I'm left with x plus 2. At the bottom, the greatest common factor, the only way I can factor is factor out of x, and I'm left with x plus 2. So what you have, let's see if I can put up a, so this doesn't get messy. All that goes with the top. All right, so now I'm over here. So what I have now is 12 times x plus 2. And that x by itself, that's like an x minus 0. All right, you don't have to write x minus 0, but if you want to, that would be x minus 0, and this is x plus 2. So automatically, when I look at this denominator, I know that x cannot equal two numbers. The two numbers that's going to make this denominator 0 would be 0 and -2. I just need to be able to classify and determine whether it's a vertical asymptote or a hole. So 0 and -2 are the two numbers that are excluded from your domain. So when it comes down to your domain, your domain would be x cannot equal 0 and -2. To determine whether or not it's a hole or vertical asymptote, you simplify the fraction. If it cancels out like the x plus 2 does, that means that what I cancel out is a hole. And then what's left over, x equals 0, is a vertical asymptote. All right, so all that goes with part B. All right, part C, we're running out of space. I'm going to come over here. So part C, we have y equals x over x squared minus 9. So same thing, I want to factor everywhere. The only thing I can factor is the denominator. This is x minus 3 times x plus 3. Let me move this out the way. So in factor form, x minus 3 times x plus 3. When I set both denominators equal, both factors of the denominator equal to 0, I get x equals 3 and x equals -3. So these are the two numbers that are excluded from my domain, and I need to write down whether or not it's a vertical asymptote or a hole. So when it comes down to my domain, I know that x cannot equal -3 or 3. So this is the domain. And then I need to simplify my fractions. Well, if you notice, nothing at the top cancels with anything in the bottom. So since nothing else, since this fraction cannot be simplified, that means that both x equals 3 and x equals -3, they're both vertical asymptotes. All right, so let me show you the graph of this. So you have a graph where you actually have two vertical asymptotes. So let's see, y equals x over x squared minus 9. So let me delete that. So y equals division x over x squared minus 9. Minus 9. So you have two vertical asymptotes. You have one at -3 and you have one at 3. All right, that's what the two breaks of the graph. Graphs, if you notice, you have those two vertical breaks. Let me actually put those in there so you can actually see. So let's see, x equals -3. So that's that vertical asymptote. And then x equals 3. So those are the vertical asymptotes. All right, so I saw that without even graphing. I did that algebraically, and that's what you should be able to do. The last part are your horizontal asymptotes. So the other asymptotes or horizontal asymptotes, it says determine other asymptotes by considering these three possibilities. If the numerator has lesser degree than the denominator, then there is a horizontal asymptote at y equals 0, which is the x-axis. If the numerator and denominator have the same degree, so we talked about that before, that means they have the same highest exponent, top and the bottom of the fraction, then the horizontal asymptote has the equation y equals, so if you notice here, they both have x to the nth power. So whatever that n is, n can be any integer value. Your answer is going to be the a over b. So you just take the coefficients of the top of the fraction and the coefficient of the bottom of the fraction, and that's your equation of your horizontal asymptotes. These are called the leading coefficients. If the numerator is of degree is more than the denominator, there will be no horizontal asymptote. So if your degree in your denominator is actually, so it says if the numerator of degree is more than the denominator, there is no horizontal asymptote. All right, so let's look at horizontal asymptote. So these are the three cases. This is just three cases that you need to be able to identify just by looking at the equation. So if you look at example 2, these are the same rational functions as before, but this time we're giving the horizontal asymptote. Oh, they're not the same. They're different. All right, good. Because it says state the domain and give the equation of any horizontal asymptotes. All right, well, since I'm only giving the horizontal asymptotes, I don't have to factor the top. Only thing I need to worry about is the bottom. So this is x minus 2 over x minus 3 times x plus 2. So when it comes down to the domain is that x can't equal the 3 and the -2. That's the domain. They asked us to find a domain. When it comes down to the horizontal asymptote part, you don't want to have it in factor form. You want to look at the original problem. So I have x to the first power and x to the second power. Since the degree at the bottom is bigger, so I have a 2 here and I have a 1 at the top. Since the degree at the denominator is bigger, this is going to be y equals 0 is going to be your horizontal asymptote. Which is the x-axis. Horizontal asymptote is the end behavior of the graph. What's happening at the ends of the graph? All right, so the ends of the graph, both sides, they're going to get closer and closer to 0. So let's see that. That was x minus 2 over x squared minus x minus 6. So let's see, y equals division x minus 2 over x squared minus x minus 6. All right, so if you notice on both sides of the graph, let me close it up. On the ends of the graph, both sides are getting closer and closer to the x-axis. So looking at both ends of the graph, they get closer and closer to the x-axis, which is y equals 0. All right, part B, the domain, numbers that make your denominator 0, x equals -1 will make my denominator 0. Draw a little bit darker. So here, since x can't equal -1, my domain is that x can't equal -1. So that's the first part of the question. And then to get the horizontal asymptote, you look at the original problem. Are you looking? So if you notice here, they both have the same degree. The degree at the top is x to the first power, the bottom is x to the first. They both have a degree of 1. So in this case, you use the second rule, which says if they both have the same degree, then your answer is going to be your leading coefficient. So it's y equals 4/1, which is the same thing as y equals 4. This is your horizontal asymptote. So if I graph this, that means both sides of the graph, both ends of the graph should be getting closer and closer to the line y equals 4. So let's see, 4x minus 2 over x plus 1. So I'm graphing this y equals 4x minus 2 over, what was it, x plus 1. So both sides of the graph should be getting closer and closer to the line y equals 4. So you can see it. Let me put the line y equals 4 up here for you. So y equals 4. All right, so notice I have that purple line in the middle. That's y equals 4. Notice on both sides of the graph at the ends, the green line is getting closer and closer to the purple line. All right, that's what a horizontal asymptote is. All right, and the last one here, the denominator, from here I know that x can't equal 1. So this is your domain. All real numbers except x can't equal 1. When it comes down to my horizontal asymptote, I notice at the top there's a degree of 1. At the bottom at the top there's a degree of 2. And at the bottom there's a degree of 1. Since the 1 is smaller than the 2, there's no horizontal asymptote. So there's no horizontal asymptote. And that's it. That's rational.